Now we're going to try to use the equations we developed for model pump analysis to analyze a centrifugal pump. So to remind you, a centrifugal pump, we've got these blades that are spinning around, and they're going to drive flow from the middle, out to the edges, and what would be pumped away. So the blade speed and the blade angle is going to change how much fluid is moved through the pump. So last lecture, we showed that for this type of pump, that the normal velocity entering, that is entering the blade region, so that would be right here, VNN, coming into the region, can be calculated based on the tip speed of the blade at the bottom, where it's entering, times the tangent of beta 1, the angle of the blade to the direct to the tangent here of the surface. So that's our equation that we determined at the last lecture. For the ideal model that we're using, there is no VT in, that there is no tangential velocity at the inlet. All the fluid is assumed to be coming in perpendicular to the surface where that defines the control volume, where the blades are actually functioning. So the fluid comes in perpendicular to this surface here, and then it's pushed by the blades. We developed an equation for the water horsepower, density times the volumetric flow rate, times U2 times VT out. So this is going to be the tangential velocity at the outlet. That is going to have a value. U2 is the blade tip speed at the exit here, at the upper edge of the blade, minus UTN, but VTN is 0, as we said in this idealized model. So for this idealized model, we won't have this term. We learned that when the net head could be calculated based on the water horsepower divided by rho g q dot. And finally, we had an expression for efficiency, which related the water horsepower, that is the energy delivered to the fluid, to the power exerted by the pump. That is this omega times the torque, the power actually exerted by the pump, how much of that power actually energy ends up in the fluid. So that's what that efficiency ratio is. So given all of those equations, let's go ahead and take a look at an actual example. So we'll give some diameter, some specifications for a particular pump, and then we'll try to analyze it. So given these pump parameters, R1 will be equal to 9 centimeters, R2 is equal to 16 centimeters. So these are the inner radius and outer radius where the blades are sweeping. The angle of the blades at the inlet is 30 degrees. The angle of the blades at the outlet is 20 degrees. The speed of rotation, given in RPM, is 1400 rounds per minute. And finally, the blade thickness is equal to 5 centimeters. So draw a picture so you know what the blade thickness is. So if you looked at this pump, we have some kind of pipe bringing fluid into the pump, and then you have the region with the blades, which would look something like this. It's a circular region. The fluid is coming in here. And then we have the blades up here and down here. They're rotating, as we described before, in and out of the page. This should be symmetric up and down. And so these are blades. And the thickness is this dimension here. So this is going to be the 5 centimeters. So our thickness of the region that has the blades is 5 centimeters. Again, we'll draw the picture here so you have all these beautiful dimensions. So we have the rotation here. This would be around some point O. R would be the axle. And so that would be your R1, where the inner part of the blade is, and then R2 would be the outer edge of the blade. And as we just said, there'd be a 30-degree angle here, and then that narrows down to only 20 degrees sort of out here where the blade ending is. So this would be a 20-degree angle there and a 30-degree angle here. So those are our 30 and our 20 for the blade angles at the entrance and at the exit, and the whole thing is rotating around at 1400 rounds per minute. So our task for this problem is to find the usual things like volumetric flow rate, water horsepower, net head. for this particular pump. So given these parameters, how much water do we expect to move, how much energy gets into the flow, how much net head pressure is available, and we have to know what the fluid is. Let's say, in this case, the fluid is our ubiquitous friend, water. So we're going to go ahead and try to do that. You obviously can start on your own if you want to, but I'm not sure how far you'll get. But we'll dive into this in the next bit.